So my name is Eran. I'm from IBM Research, and I'm going to talk about bringing compute to Swift. I'll really try not to say the word Docker too many times. So what do we mean by bringing compute to Swift? Swift, OpenStack Swift. How many people have touched Swift, know about Swift, used it? Or, OK, I expected more hands, but fine. So the storage engine, which I'm going to talk about, extends the OpenStack Swift by enabling the push down of filtering, transformation, and analysis tasks to the Swift instead of bringing the data to the compute. So what do I mean by that? Imagine the arguable yet simple following example. You have a bunch of movies, high-definition movies in your Swift cluster. You want to download them from a low bandwidth mobile phone. So instead of copying it to a proxy and then do some transcoding to reduce the resolution, you just run a transcoding task inside the Swift cluster that takes this HD video, reduce the resolution, and then you can download it to a mobile using a lower bandwidth connection, right? So the idea is to run question.
What is the difference now between Swift offering current engine and Hadoop? You're actually running all the data.
Right, so let me try and come back to that, OK? There are many differences, but I'll try to come back to it later. Right, another point. Note that filtering, transforming, and analysis, we're talking about tasks which can be done stream-like. So that if you want to take a 1 gig object and sort it, you need to load it into memory, sort it, and then only then you can bring it back to the user. The idea here is not to do that. The idea is to use streaming so that the user doesn't need to wait for the response to come. And you don't need to utilize too much memory while at it. So for this, the actual machinery behind the storage engine is what we call a containers-powered Swift cluster. So what is a container-powered Swift cluster? First of all, it's a Swift cluster. So here's the Swift cluster. We've got a proxy tier, which is the tier where client request hit. There is the storage tier, which is basically commodity servers with a lot of disks inside. And on top of that, we put on some sandboxing technology. Think Docker, think LXC containers. This is what we've experimented with. So why do we need sandbox here? And this is one difference relating to Hadoop, is that eventually you want to allow the user to upload the computation. So it's not something like someone can verify in advance. We want the user to upload the computation and then run it over his own data. So we naturally need to run the compute inside some kind of a sandbox. So we've got a sandbox there. Naturally, that sandbox needs some image. That's the image. That's the sandbox. And we need one more thing, which is a piece of middleware that would be able to route the Swift data to the containers. Right? We need some glue so that the Swift data, as it flows in or out of the object store, we can actually route it through the computation and then either put it into the object store or take it back. So we have that machinery in place, and now I want to kind of illustrate how things work end to end. So we have all this set up, and now there is some developer who wants to code some task to be uploaded to Swift to be used as a task that can run over Swift data. So this is what, by the way, we call a storlet. So a storlet is a compiled code that can be uploaded as an object to Swift to be later on invoked over Swift data. We chose to begin with Java, which we believe is widely adopted by lots of developers. So if you want to implement a storlet, it's very simple. You basically need to implement that single API. You don't need to delve into all the details. The point to make here is that there is an in-stream, there is an out-stream, which are the input and output of your storlet. You get the in-stream, which is either an object that's already in the object store, or is some data that is being flowing into the object store. And then you consume it. You do whatever transformation over it. You write it into the outstream. You code this. You wrap it as a jar. And that's your storlet. Next step would be to upload the storlet into the system. So one nice feature here is that storlets are treated as simple objects. So all you need to do is to do a put operation. That's a standard put operation to Swift. You can see here the v1, which is the version, the name of the account, the container to which the storlet is going to be placed in. So this is a designated name, right? This is the name where our system will later be looking for the code in order to run it. But again, we're in the step where we just upload it to the system. So we upload it into a designated container, in this case called storlets. And this is the actual storlet that is being uploaded here, a watermarking storlet. I hope I'll be able to demo it later on. So this is uploading a storlet. Once it is uploaded, you can invoke it over data that already resides in Swift. So there are two ways to invoke storlets. One of them is while getting the object out of the object store, and the other one is put. So what does it mean to run it as part of a get operation? The idea is that I don't want the object as it is kept inside the object store. I want a transformation over it. So I'm doing a get. Again, this is a simple get as any other get in Swift, only we're adding a header here called extra storlet, in which case we are running the watermark storlets. So we're not going to get the original video here. We're going to get the video after being processed by the watermarking storlet. So how does it work? We do the get hits the proxy server. The proxy server, as it does with any other request of Swift, picks up one of the object servers that holds a replica of that object, in this case, mov webm, and then we will kick in. So this is like a zoom in into this node. On the left-hand side, we see our piece of middleware. On the right-hand side, we see the sandbox that is going to execute the storlet inside. First thing we do, we intercept the request. Not drawn here. There is kind of an initialization phase where we realize that this storlet, the actual code, the jar, isn't yet on this, inside this container. So we need to bring it from Swift. On the first invocation of the watermarking storlet, in this case, we bring it from Swift. We install it inside the sandbox there. Once it's there, we can invoke it. So here goes the invocation protocol. I won't get much into details here. I do want to stress out this arrow here. We pass an input and output file descriptor from the Swift side, from our middleware, to the container. The point I'm trying to make here is that the container is completely blocked from any external I/O. We use the non, referring back to the Docker talk, we use the non-networking. We have no access to any other I/O devices. The container only gets those file descriptors at runtime of whatever he needs to be able to process as input or output.
So can you repeat this? So what is container is able to do only to get to the block or object currently being processed?
So imagine we're in the get. So we're in the get operation, right? So I'm going to talk Swift a little bit here. If we're in the get operation and we're inside the object store, what we have in hand inside Swift, right? Not inside the, not here, but here. We got a file descriptor of an open file, which is the object that appeared in the get operation, right? We take that file descriptor and we pass it on to the storlet running here. So the storlet can actually read the file.
On the same machine?
On the same machine, of course. This is the same machine. This is, as I mentioned, the zoom in into that machine here. Right, so we pass the file descriptor. The storlets here do whatever it needs to do, send us back through the file descriptor. We passed here the output, and we can continue the regular get flow of Swift, right? So we just added the middleware, no other interventions, and we're able to do this. Here's the flow of a put operation. So in a put operation, what we want to do is we don't want to keep inside the object store the actual data as it is being uploaded by the user. Rather, we want to keep a transformation over it, or perhaps metadata enrichment of it in the data store. So in this case, you see a regular put. Again, the version, the account, the container, the actual data, and the extra storlet. In this case, metadata extractor storlet, which illustrates a use case where all the storlet does is looking at the data, extracts some metadata over it, and enriches the object's metadata as it appears in Swift. This is like more for Swifters, perhaps, remark. So again, in this case, in the put case, we kick in inside the proxy server. Why? Because as you know, in Swift, every object is going to be created 3 times. If we were to kick in inside the object store, we would have done the calculation 3 times on each of the replicas, right? Maybe wrong, but OK. So anyway, we kick in the proxy server. We pretty much do exactly what we did in the object store. Only when we're done, we continue with the proxy put flow, which basically going to do replication to 3 different object nodes, and we're done. I was told that there are networking problems. I will try to run the demo. Let's see if it works. OK, it might just work. So it's kind of tricky. I'm going to show a watermarking stalled demo. So we're going to do a get operation to a movie. And we're going to stick a watermark on it. OK, let's see first if it works before I. Where's the backspace here? Try to skip that. I hope it'll work. No. Whose laptop is this? It's yours? You don't need to worry about malwares here, but let's see. I'll try one more time. Otherwise, we'll just keep the demo. Oh, here it is. OK. Thanks. Questions in the meanwhile? Any questions? Yep.
You mentioned the type of thing, and you also mentioned that you use Docker and Docker containers. So Docker containers are not secure. So I didn't understand the part what you mentioned about sample thing.
OK, so when you're saying they're not secured, in what way they're not secured? We're getting.
It's possible to break out of the container to the host. So if you run malicious Docker job, it can break out and delete all the data in Swift.
Right. So there are actually 2 answers to this. One answer is to say that we trust the Docker community or the Linux kernel community to eventually fix such issues.
No, it's fixed. You need to run Docker inside KVM. This is the only solution for today.
For today, OK. So I'm not saying that currently this is the most secure solution that you might have. I'm not a security expert, but I'm assuming that what you're saying is even if I use like user namespaces, I'm not running as root. I don't have any IOs exposed, any IO devices exposed. I can still break it. This is what you're saying. OK, good point. Need to fix that. But I think that one of the points to make is that we're not really tightly coupled to Docker containers. This is what we've used in our POC. This is an experimental stuff, right? It's not like anything mature here. So you can plug in a VM there. You'll get of course, you'll get suboptimal performance there, but filtering, transcoding to some extent. Again, it's a question of how much hardware are you willing as an operator to throw in there, right?
It's also one of the chances that are actually file execute the code, because in many cases the file itself is contained in the
Right, so the question here about fragmentation of the file. So, right, so in Swift, basically, up until the introduction of erasure coding, you were promised that, I mean, it was a characteristic of the system that the object would reside as a whole in a single file inside the object node. Now, when EC is introduced, which is erasure coding, then actually a single object is being broken into several pieces across many nodes, in which case you can do the task on the proxy server, because the proxy is going to assemble all the pieces, right? Now you can argue whether, OK, so you're not running exactly where the data resides, but you're still inside the cluster. Another point here is encryption. Also, in encryption, the decryption would take place on the proxy server. So once again, you need to do the processing on the proxy server. Yep.
Can this be used to deny get supports?
To, sorry?
To deny get supports.
To deny gets or puts. I believe it can, but then you can't, you mean to sort of enforce some access control policy?
For example, say it's
So it's a nice, OK, so it brings me to a nice use case that we've done here, which is, OK. OK, thanks. So I'll just answer that one. If you have the out-of-band management of this access control, naturally, why not? I mean, as long as the Stolet knows what to do, of course. Another nice thing that we've done here is, or another nice use case for Stolets is what we call anonymization. So suppose that you have like medical records or pictures that, in one hand, you don't want to block the retrieval altogether, but you are willing to anonymous users to retrieve them, but anonymously, right? So you can run a Stolet which does anonymization, and actually you can run it according to the access control being defined over that object. So our middleware can look at the authenticated user, and if that authenticated user does not have access to the object, give it access, but run the Stolet before you return the data, the anonymization Stolet. So this is another use case.
Question about in continuation of the same issue. Isn't it too late to do it when you are getting to the data? Don't you want to make a ACL anonymization as close as possible to the user, to the API?
I would say the opposite. I would say the opposite. In some cases, think about medical records, right? Where you have Swift to keep those medical records, and then you're doing the anonymization somewhere outside of Swift that is aware to some kind of access control policy, who gets to read what, right? So some people will argue that they don't want the sensitive information to ever get out of Swift. So I would say the opposite. I would say do the anonymization as close to the data as possible.
So maybe it should be done in conjunction.
OK.
ACL check should be as much as close to the user, but the filtering itself can be done.
Sounds reasonable. Right. How much time do I have? I think plenty. 5 minutes. OK. So the code is in the open. That's the link. There's a lot of documentation there. If you do intend to play with it, I would recommend start with the S2AIO. That's Stolet Swift all-in-one. It's gonna provision a VM for you, installed with Swift and the Stolet engine on top, and you can play with it. Another point to make here is that public users will be able to experiment with the Stolet engine thanks to the Fireword. That's an EU research project that is gonna actually allow public users to experiment with Stolets. Let's see if I can. So this was my backup for the non-working demo. That's another set of use cases that we've experimented with RAI. RAI is Italy's national broadcaster. This is something that we talked about in the Paris OpenStack Summit. So quickly, so here's the idea. So the whole notion of this is how to take a media workflow and move it into the clouds, which is something that was mentioned this morning by Jonathan. So you take an MXF. MXF is a format for media files. You take the MXF and you upload it to Swift. And you do this put through a metadata enrichment stolet. So what that metadata enrichment stolet, he is aware of the structure of the MXF, and it can extract certain metadata that has to do with media, of course, and enrich the object metadata. So Swift has a notion of object metadata, user-defined metadata. So whenever you upload an object to Swift, you can add their metadata. All sort of stuff you want to describe your object with. So this is done upon a put. Now, once you have this metadata enrichment, this is something that I haven't talked about. We also added a feature which is metadata search, where external users to Swift can actually do search of objects according to their metadata. So suppose that you've done that search. Sorry, let's forget about it. I'll get back to it later. Another thing that you can do is then calculate the loudness normalization of the object. So this is a hot topic apparently in the media world, where different files have different loudness. And so you start to hear something in acceptable volume, and then the volume drops, and then it goes up again. So a lot of the videos they have needs to go through a loudness normalization. So what they do here is they're running upon get. They're running what's called the loudness calculation stolet, which goes over the movie, calculates a number, which basically says whether the loudness is OK or not, whether it needs to be normalized or it does not need to be normalized. And they also add the calculated value to the metadata. Then they can do a metadata search looking for all the objects that have a bad loudness normalization value, and then run the fixed loudness stolet, which basically reads the movie, looks at the movie, do whatever calculation it needs to do inside the object store using stolets, normalize the data, and then save the object again back to Swift. Sorry. So I'll try now to answer the question that was raised regarding Hadoop. So as I mentioned, so in Hadoop, you're kind of tied to the MapReduce model, right? You need to program either map or reduce tasks. Here it's kind of free, right? You can program whatever you want. Another thing that I haven't really talked about, because I was asked not to talk too much about Docker, is that your stolet might be dependent on a non-trivial software stack, and we do allow here, and the model does allow here to each tenant admin to upload his own Docker image, so that if you have like a dependency on I don't know, JDK 6 or JDK 7, you can make sure it's there by uploading the appropriate image. I think that another difference is that in the real world, at least this is what I heard, usually people do not run Hadoop tasks over their production data. Because usually the production data, this is like a second hand, right? I'm not an expert here. This is something I heard. So the production data, lots of times need to go through an ETL, an extract, transform, load process, where many times the time that takes to the ETL is many times to understand what's the format, what's the right way to do the transformation. And only then, once understanding what ETL needs to be done, they do the ETL from the production data to a specially provisioned Hadoop cluster, and then they run their Hadoop. Right, so this is a different use case. It's an object store. You can argue whether it's not necessarily production data. It's a different type of data. I would say it's a different world. Time to more question, or we're done? So, yeah.
Swift itself written in Python, right? And you use Java installers. So how the fact of two different runtimes, is it a plus or minus, advantage or disadvantage?
Good point. So when we're in an effort to upstream this to Swift, and this is obviously a question relevant in this direction. So what we actually do is that we have isolated a very thin piece of Python code, which is the middleware that actually goes into Swift, into the pipeline of Swift, right? But all it does, it's kind of a hub routing, eventually file descriptors, but routing data from Swift, out of Swift, and from out of Swift into Swift, right? So this is a Python, this is Python code. Whatever whatever lives outside of that, where it belongs, it's a good question. It's not part of upstream Swift. Maybe it needs to be on StackForge, maybe whatever. But it's absolutely, but you're right, it's not part of Swift. This is the part of Swift, which is relatively small to all the things that run here.
Also, in my opinion, Java is not a good tool for video and image processing. So you need native code for it.
Another good point. So adding other programming model is relatively easy. All you need, the characteristic we need from the programming language is very simple. Take a Unix domain socket, take a Unix file descriptor and wrap it in the native language stream, and you're OK. So you can do Python, you can do, I don't know, pretty much everything. So, OK, so we've been approached by one of the core members from Swift, who is from Intel, and obviously have motivation to put it into Swift, because they'll probably be able to sell more cores into the nodes there. There are different opinions in the community, so some of the guys think everybody accepts it's cool, right? But then everybody asks the question, does it really belong into Swift? So if you ask the core from Intel, he would say yes. If you ask the other member, they would probably say no. Perhaps this piece belongs there, the other, probably not. So currently, where's the, currently it's on GitHub. So it's kind of a read-only. We will try to make it like a public project where everybody can contribute. Currently, it's more like for experimentation, and it was developed by IBM, yes. But we'll be happy to make it a community project. I will be happy to make it a community. Right, so we're out of time. Thank you.